All right, let's start. The speaker today is Professor Qixing Huang from UT Austin. His research is quite deep and broad, so including like graphics, geometry, optimization, vision, and ML. So it's really a broad spectrum. He has published more than 100 papers and leading venues, and he has won multiple awards, including NSF Korea and E.G. Kai Early Career Spotlight. So he has been also area chair and senior area chair for multiple leading graphics and vision and ML conferences. So thank you, Qixing, for coming.
Okay, thanks. Can you hear me? Okay, so what I'm going to talk about today is something that I have been doing for 2 or 3 years, very recently. Okay, so this is in the space of generative AI, which is one of the hottest topic right in industry right now. So I'm a 3D person. So in my field, a central topic in the generative AI era is to learn generative models, right, that map a latent space to the space of like memory shapes, deformable shapes, and 3D scenes, right? So those generative models have a lot of applications, right? In particular for solving inverse problems. Like before the deep learning era, we have like simple model, right? Or escape, widely used. But of course, this field has been changing rapidly due to breakthroughs in machine learning models, okay? So including GAN, VAE, autodecoders, and very recently for diffusion models, okay? So there's a common thing among those diffusion generative models. They try to solve the so-called distribution alignment problem, right? We have some data that define the so-called empirical distribution, and we have some induced distribution defined by the generative model, okay? And we want to align these two distributions, okay? So this is a very challenging problem. We have made some progress so far, including the machine learning models I showed in the previous slide, okay? So those machine learning models have been applied in the 3D space. So first of all, to do machine learning on any machine learning, okay, on 3D data, we have to solve the representation issue, right? How to encode 3D data, right, in those standard forms like matrices, vectors, sets, or graphs. So this is a very exciting field. So for all the representations, 3D representations, we started in computer graphics. We have at least one, sometimes a few, okay, well-known new representations, okay? So this is exciting. And we also have this triplane representation, right, which was introduced to bridge 3D generation and the image space, right? So overall, this is very exciting. But on the other hand, if you look at 3D generation from the machine learning perspective, okay, this is not that exciting because what has happened so far is that whenever in the image and video generation community, people showed good result for some machine learning model, okay? Then in the 3D space, we adopt under some representations, okay? So we did this for GAN, for VAE, for autodecoder, and for diffusion models, okay? And we can go this again, right? So, for example, very recently, we have flow-based generative models, right? Reactive flow was introduced by my colleague, okay, at UT. So you can do this, right? But my argument is that this is insufficient, okay? Because from the application perspective, there's a huge difference between image and video generation and 3D generation, right? For image and video generation, we care about visual quality, right? And because of visual perception system, if you do distribution alignment at the patch level, okay, then you can generate very realistic images and videos. This is the reason why diffusion models are very successful, okay? But for 3D generation, in particular for shapes, we care about a lot of priors and attributes that we do not talk about on 2D data, right? So what are those priors? So one application of 3D generation is in manufacturing and 3D printing, right? About a decade ago, at SIGGRAPH, each year we have like 4 or 5 papers, right? How to design 3D models that are 3D printable, right? If we do that, those models should be physically stable, right? Otherwise, we will run into issues, right? But if you, this is very difficult to enforce, right? If you do 3D generation, okay? We care about topological priors, right? The shape has to be connected, should not have many small holes, and this is also very challenging to do, right? Under standard shape generation. And we have deformation priors, right? In particular for deforming objects. We have some underlying skeleton, right? The intershape deformation should have, should be articulated, okay? So this is also difficult. So if we just do generic distribution alignment, right? So the network architecture certainly does not model those priors. In the training approach, doesn't model, right? The standard distribution alignment. So it's very difficult to enforce those priors, okay? So one argument is that maybe in the 3D domain we have very limited data and we have those issues. Maybe we have, suppose we have sufficient data, then we will not have those issues, right? So let's look at the Sora model, okay? So we can see that it generates very realistic videos, okay? And this is particularly true because of the human perception system, okay? But on the other hand, the amount of data, okay, and the amount of compute to train Sora is only a few companies that can afford, right? So this is not really a scalable approach. But if you look closely, right, so we have the notion called perspective geometry, right? So we do have perspective geometry, including vanishing point and straight lines in the training data, right? So, but if we use a CNN-based architecture to do some kind of interpolation, right? That is what geometry models, okay, do, right? So we do not preserve simple geometry structures, right? So my argument is that if the geometry structures are important, for example, if we use synthetic data to do 3D reconstruction, right? For sure, if we just care about visual quality, you may not care about this, right? But for certain applications in which geometric structures are important, there are a few of them, then, right, this becomes an issue, right? So if those simple geometric structures cannot be preserved, even using a lot of data, right, we have to figure out a way to enforce 3D priors, right? So today I'm going to talk about how to enforce 3D priors, okay? I will begin with how to do so by developing neural networks, right? So this is something that case by case. We do not have a theory behind this. It's very limited, but I still want to show some limited results, which are interesting. And then we'll focus on how to develop regularization losses, right? Better training losses to alleviate the issue, okay? I will start with network design, right? So I will talk about 2 papers. The first paper is about a shape decoder by enforcing some very simple geometric insight. Okay. A second paper, and I think so did by my student, the first author, and the main idea come from Noel Augerman, who is at Miller. Okay, so it's a wonderful junior faculty. Okay, so this also has some geometric constraint. Okay, enforced by during a neural network design. Okay, I'll talk about those two papers. Okay. Okay, the first paper, what we want to do is to think about how to use MLP-based implicit representation to decode the 3D shape, right? So this is something if you work in this space, you should know, okay? If you know NERF, right? So NERF uses MLP, right, to decode density and the color field, okay? The second thing to do here is that we train MLP, right, that takes a position as input and output a sign distance value of this position, right? The shape is the zero-level set of this function, right? So this was introduced at CVPR 5 years ago, right? But there are certain issues, right? For example, one issue here is that if you do this to generate chairs, okay, you need the training shapes to be consistently oriented, right? The front or the upright orientations should be given, okay? Otherwise, it doesn't work, okay? Right. Okay. So what we want to do here is to generalize this idea locally, right? So we want to train a local MLP, right? We describe the cell space into cells, and with each cell, we train a local MLP, right, to decode the shape in each voxel, okay? But we want to have some geometric insight, right? So what is the geometric insight? So we know that if we have a 3D shape, right, locally we have the notion called tangent plane, right? Locally, a surface is a plane, right, defined by the normal direction. And also, if we increase the neighborhood a little bit, it's a quadratic patch defined by the coordinate system, right, using the normal and the two principal directions, right? Okay, so locally it's a quadratic patch, and we also know that the sign distance function of a quadratic patch is a quadratic function, okay? So the idea here is that, so within each cell, we want to decode the sign distance value of a point. What do? We transfer the point in the so-called coordinate frame, right? Then we decode, right, the sign distance value. In theory, we just need a quadratic function, right, if we do this. Without transformation, then the MLP has to encode quadratic functions of rotated copies of this patch, right? So this is what image convolution networks, right? The first few layers, we have the edge detectors at multiple orientations, right? If we factor out this orientation, then we just need one MLP, right, in theory, right? So it's a very simple idea. I'm quite surprised that this has not been explored in the 3D space, okay? Okay, all right, very simple idea, right? So what do we do? During the training phase, we optimize a shared MLP, right? MLP takes the latent codes that encode the geometry of the surface patch, right, upon a latent code, right? And optimize the coordinate frame for each cell, right? So during the training, we optimize the coordinate frame, right? Initialized by the PCA, right, to predict the normal and principal directions, okay? And that becomes also very important, okay? So then we optimize the MLP, okay? Shared MLP. Then during inference, for example, when taking a point cloud as input, we vocalize the point cloud, we freeze the MLP, we optimize the latent code of each cell, and the coordinate frame of associated with that cell, okay? Then we decode the shape, okay? Right? Another insight is that we need to use quadratic layers, okay? Because the scientific function locally of a quadratic patch is a quadratic function, right? You compose linear functions, right? Even using MLP is still linear function locally, right? We have to use some quadratic functions at some layers. And that is also important, okay? So that is the basic whole idea, very simple. Surprise, nobody has done this, okay? Okay, let me just show you some results. So using this, we reduce the size of the MLP, right, by 30%. We only need to use 30% of the parameters, okay, for the MLP, right? And we have significantly improved generalization error, okay? Okay. So another thing is that how to initialize the coordinate frame, right, to do the training and to do the inference is very important. We have local minimums, okay? We have to initialize using the PCAs, right? In particular, normal direction is important. Otherwise, we still get some improvement, though not very significant, okay? If we initialize using PCA, then it's significant improvement. And using quadratic layers also improves, okay? And the generalization error is reduced, okay? Okay, some visualization result. So right now we are using this representation to do shape generation, right? So this is representation, neural representation, right? We did not do shape generation, okay? There are a few issues to address. So this is one example why, in which geometric insights are very important, okay? If you know some principles, okay, of the data, okay? Right? The principle is that if you know a little bit differential geometry, like 1 week, okay, you should know the notion of tangent plane, like quadratic patches, okay? So this is very basic stuff, okay? Okay, and this is very important, okay? Okay, the second paper, I want to talk about turtlenet. I think Ed, you, okay. Yeah.
What is captured in the latent code? I was just curious about. In the previous paper,
Yes.
Was there a way to visualize what's captured in those latent codes to understand why they were being helpful over deep LS?
Well, so that is actually a very good question. We did not do the visualization, but at least if you look at this, right, so by applying the coordinate frames, the size of the MLP is significantly reduced. At least we know that we factor out some rotated copies of the 3D shapes. Otherwise, this will not happen, right? Right? That is the only insight we know, but we do not visualize. So the reason here is that, I mean, in theory, this is guided by the notion of tangent planes, but the size of the voxel is not very small, right? It's like 32 cubic, right? So we have some non-trivial shape in the local patch that is not explained very well using like this kind of quadratic patch, right? But the idea here is that we factor out rotated copies, okay? Okay.
Okay, thank you.
Yeah, yeah.
I have a related.
Yeah.
The patches are apparently not IID, but when you train the MLP.
So basically, the patches, when training the patches, they overlap a little bit. The support vision extend to neighboring cells, so that we do have some continuity between the JSON patches, right? So
that makes the problem even worse. The patches are not IID, but in training you sample the patches in an IID function. So I'm wondering what's lost when you enforce that.
So what do you mean by IID?
Independently, identically distributed. When you sample using whatever training framework, you are making that assumption implicitly, right?
Well, so essentially we want to, so the idea here is that we want to know a local shape prior, right, from patches of training data, so that, I mean, even the amount of training shapes not that big, but if we have a lot of patches, and that should be sufficient to know a shape decoder, right? So we see enough data, right? And during inference, we optimize latent code. I don't really understand why we have the IID issue. Okay, maybe take this offline. Okay, okay, right. Okay, the second paper, what we want to do is to look into deformable nerve, right? So standard, right? So this is widely used, right? The standard thing in nerve is that we use near field to decode the color and density, okay, and to do null-view synthesis, okay. But if we have a deforming object, what we do is that we apply the deformation between the deformed frames and the canonical frames, right? And then we know a nerve in the canonical frame, the near field, right? Then we use the deformation to determine the density of color field at the deformed thing, right? Like, to do null synthesis, okay? So if we do this, the mapping between the canonical frame and the deformed frames should be one by one, right? Otherwise, we will have this kind of, like, we aggregate 2 points in the canonical frames, right? So then we have some fuzziness, right, when doing null synthesis, right? So this mapping should be one-on-one, right? So that is the issue we want to address, right? Without injectivity, we have this fuzziness because we aggregate the values of 2 points or multiple points. If we have this injectivity, then it's much better, right? So that is our goal, okay? So we want the injective map and a very flexible, accurate map that can model very complicated deformation, right? So this is something very difficult, okay? If we want to have a volumetric mapping that is one-to-one, it's very difficult, okay? We have very limited theoretical result, okay? It's very complicated to enforce this, okay? Right, so our idea is to do this in 2D, then leave the 2D deformation in 3D, okay? So reason here is that in 2D, we have the notion called turtle embedding, right? So the other you must be familiar with this, okay? So we have, suppose we have a convex domain, okay? It must be convex, for example, square. And we change the boundary condition, right? Right? And we solve the graph Laplacian, right? To get the embedding. If it's convex, if the boundary does not have the flipping, it's a flip, the order should be preserved. Then you solve the graph Laplacian, and the mesh is real to be self-intersection free. We do not have this result in 3D, right? This is on 2D specific. Right? If we have this result, what we do here is that for any points, we locate the point in 2D triangle, then we lift, then we get 3D, right? We get 2D deformation continuous, right? Right? How to control the 2D deformation is that we can control the locations of boundary vertices using a neural network, right? For different networks, they have different locations of the boundary vertices. Then we have different 2D deformations. Now this is right. So this is by construction. Okay. Now very simple idea, right? So how do you generalize this idea to 3D? Because we have neural networks that have multiple layers. This is a very simple idea I really like. Is that we can choose the plane, right? We can choose the z-axis, right? So we can compose, right? One layer, we do the deformation by fixing one coordinates of one axis, along one axis. We do the deformation in the remaining two coordinates, right? Then the next layer, we change to another axis, right? We do the deformation again, right? And we can compose them together, okay? So we do not need, right, many such layers, okay? Typically 20 layers to have a compressive, to have a very expressive 3D deformation, right? So this is the example, okay? One layer, the other layer, right? If we compose those 2D deformations, okay, we can have a very expressive, okay, 3D deformation, okay. Very simple idea, right? By construction, right? Okay, right. So this is the deformed nerve result, right? So you can check the paper. I think the code is released. Visual comparison, right? Without this, we have a fuzziness, some weird stuff, and with this controlled deformation that is guaranteed to be one-to-one, we have significantly improved result, okay? And we can also do this to deform a 3D shape, right? If we deform a human, right? How to enforce that we do not have self-penetrations is very important, right? And this is guaranteed. Of course, we have to add some regularizations to preserve the as much as possible, right? But one-to-one is guaranteed by construction, right? So this is very interesting. So I think I showed two examples. So in generally speaking, I think how to find the balance between geometry insight and machine learning is very important, right? We do not have any theory to do this, right? So this is very limited. It's very case by case, but certainly we should do, right? So I'm going to talk about enforcing regularization losses, right? So this is more general, has been applied broadly, right? So if you're working in machine learning, you may want to argue that this is just injecting inductive bias, right? It's simple, right? But it's not easy for three reasons. The first reason is that although we developed many tools in graphics to enforce geometric, topological, and physical priors, it's not easy to incorporate into learning, right? They have to be differentiable. But that is not the only concern, right? Another concern is that they have to be stable, right? Because when publishing a graphics paper, okay, even myself did this, right? We pick 8 to 12 models. We show that our approach is better than baselines. Then we publish a single paper, okay? Most of people did this, including myself, okay? If we release a code, the code works for 90% of instances, that is good, right? But if you want to do this in training, during the training procedure, you have one failure. It's not good, right? The training procedure crashes. So we run into this issue, okay? We had this idea in 1 or 2 days, and we spent 1 year to make some computational topology tools to be very robust. Okay, topological paper. Okay, so this is very important. It's very engineering oriented. Okay, many people do not realize this. The second issue is we are learning diffusion models, right? So how to enforce those priors under diffusion models, right, which have very specific training objective, is very challenging, right? The third challenge is how to ensure that the training laws does not compete against the regularization laws, right? So I will mention why this is the case. Okay, so I will start with deformable objects. I will talk about two papers. Then I think I will have time to talk about this work a little bit. Then I may not have time to talk about the computational geometry. Okay, anyway, okay. So this paper is about learning a deformable shape generator using graph neural network, right? So we have a graph neural network that takes Z and outputs a triangular mesh, right? The mesh topology is fixed. When you change Z, you change location of the mesh vertices. There are many landmark results, including 3D MM, mesh curve, right? So if you do standard distribution alignment, right, because of limited training data, if we interpolate the shapes in the latent space linearly, you get a smooth interpolation, but the interpolation does not preserve the bone structure, right? Because this is not a model, right? So what we want to do is to develop a training loss to enforce this, okay? The motivation here is that neural networks are over-parameterized, okay? The way to train neural networks really matter, okay? Really matter, okay? Many people do not believe this, right? Data solves everything, okay? I will show some interesting numbers, okay, later, okay? Okay, so what we want to do is to develop a loss so that the resulting network, when doing the interpolation, preserves the bone structure, okay? To do that, we need a deformation model, right? So here we use the AIP deformation model. If we work in graphics, you should know this, okay? So this is widely used. The idea here is that you have mesh in the one-way neighborhood. You ensure that it's approximate rigid deformation, right? Globally, the rotation is not shared, right? So it can have a non-rigid deformation, right? So this is a well-known model, and also widely used in solving inverse problems, right? In the vision community, okay? The vision people, I believe many of them do not have a geometry background, right? So what they do, right? If you have a 3D reconstruction like a bird, a human, then you minimize the AIP deformation between the reconstructions and a template, right? That is a loss, right? So this is not very good because even like the simple shape space, right? We have non-rigid shape variations that are not AIP, right? If we minimize the deformation between those shapes and template, the loss will compete against fitting the generative models to the training data, right? Okay, so how do you address this issue, right? So what we do here when training a generative model is that we are doing this generalized active contours, right? How many of you know active contours? All of you, right? I'm very surprised. I asked students at MIT, right? Like less than half, actually, they know this. Very surprised, okay? And this should be taught in every undergrad computer vision class, okay? So we do have a logic here, right? So in active contours, we have some observations in the image, and we want to fit a curve to those spots of observation, right? So here we have some data points in some space, right? And we want to fit a high-dimensional curve to those samples, right? Those training shapes are data points, right? So in active contours, what do people do, right? We have some observations, right? Those define the data terms. Then we have some regularization terms, right? Which are defined locally, right? Right? The edge length, the curve length, and the curvature, right? Those are local quantities, right? So those regularizations, if we do those, they will not compete against, right? Fitting the curve to the data points, right? At least we do not have this issue, right? See this issue in practice, right? So that is motivation, okay? So we want to generalize this idea, right? To generalize this idea is that, so we have two adjacent synthetic shapes, right? We have z plus epsilon times y, right? We have two adjacent synthetic shapes, and we want to minimize the AIP deformation between them, right? So if we do this locally, this loss will not compete against fitting the generative model to the shapes which have very large long-range variations globally, okay? So another advantage of doing so is that the standard ARP deformation that doesn't really have a closed form expression because you have to optimize a rotation, right? But if we do this locally, you can linearize the rotation, right? If we do that, I started this in my PhD thesis. Of course, at that time, I did not realize that this can be applied to train a generative model, right? So what we did, when we linearize the rotation, we arrive at the quadratic energy, right? So it's a very simple math. So I used the eigenvectors of that matrix to do shape segmentation, okay? So now we can use this quadratic energy, right? So J is a Jacobian of the generative model. HR matrix is a sparse matrix from the AIP deformation, okay? Then what we do is that in each batch, we have some training instances. Also, we sample some latent codes. Then we minimize this energy, right, from the latent codes and some tangent directions, okay, samples in Y, right? We did a slightly more complicated stuff, but I'm going to skip this, okay? Then we minimize this, okay? So we did this for evaluation on 3 benchmark data sets. So this is a table I really want to show, right? So we applied this regularization on 3 architecture, right? Comma was the earliest, right? It's very unrestricted, right? Mesh curve tries to model deformation structure in the architecture, right? Kind of like enforcing some deformation, right? The scaling structure in the mesh deconvolution neural network. So without regularization, mesh curve achieves the best result, right? But without doing so in the architecture, we add the regularization, comma, adding the regularization achieves the best result. So this is very interesting because, so if you do this using architecture, because the ARP deformation is approximate, right? It's approximate, right? We do not really understand what are the variations, violations of this articulate deformation, right? So doing so using a regularization loss is better, okay? Okay, so this paper I want to skip, okay? If you're interested, you should read. So we used this deformation model to derive a Riemannian metric and use this Riemannian metric to do linear space design, right? This is very important because we add some control in the generation procedure, right? Adding control in generative models is a very hot topic, okay? But for the interest of time, I want to be able to talk about this. So I want to spend 5 minutes to talk about this paper, how to learn the generative models from raw data, right? Because the AIP reg requires consistent meshes, okay, to train the generative model, right? So this assumption is too strong, right? We can only use synthesized data from the simple model, right? to train. A question is, can we actually train this fund data without correspondences, right? Point cloud, okay? So first of all, so what is the representation to do this? So this question is easy to answer, right? We use implicit representation, okay? And in particular, people actually try this deformable object, right? But then you realize that we cannot have post variations, right? For example, training generative models of chairs, they need to be considered oriented. Otherwise, it doesn't work, okay? We have the same issue here, right? So this is the teaser figure of that paper, right? It works if you do not consider post variations. Otherwise, we have serious generalization issues, okay? This is understandable, okay? So what we want to do is to add regularization losses, okay, to train a better implicit generator, okay, to have much improved generalization behavior when we have post variations, okay? All right, so one way to do this, if you're familiar with dynamic nerve, is you use the so-called Qixing vector field, right? But if you do that, the regularization is very weak, right? In particular, if you really want to generalize the idea to like locally A-fund deformation, right? That quite probably in man-made shapes, then the Qixing vector field approach does not apply. So the only way to address this issue is to solve the correspondence problem, but only locally, right? Because if you have a local parameterization, then essentially we can apply the AIP reg idea, right? So we only need to do this locally, right? So what we do here is that we triangulate an implicit shape, synthetic one, into a triangular mesh using a matching cube. Then we find correspondences of the mesh vertices adjacent implicit surfaces, right? If we have that, then essentially it's very easy to apply the AIP reg. Right? It's very easy to do because locally we have a mesh, right? A generative model, okay? Now, how do you build correspondences between implicit surfaces, right? So this is something that in the graphics community, in particular if you're doing physical simulation, using never set method, right? You should know this. But there's certain issues, right? A standard way, in particular in the never set community, right, doing physical simulation, is that you perturb the point in the normal direction, right? Because otherwise, the corresponding point can float on the surface, right? You only have one constraint, right? You have 3 degrees of freedom, right? So this is one way, right? But you do this, for example, if the sphere is under translation, then you cannot recover the translation, right? So this paper figured out the way, right, to address this issue, okay? So what we want to do here is to solve optimization problem, right? So we know that the correspondences should minimize some deformation energy, right? Because we want to enforce some deformation energy between adjacent shapes. We know that the correspondence should minimize this, right? And locally, we have some quadratic energy, right? Another advantage of doing so locally. And we have some linear constraints, right? By linearizing the implicit surface constraint. So we have a quadratic energy and a linear constraint. We have a closed form expression, right? So essentially, given the mesh vertices, we can pre-compute tall matrix. So the equation here is very complicated, but you can only need to pre-factorize a smooth matrix, right? It's not that computationally expensive, right? Once you have tall matrix, you can find the corresponding vertices for arbitrary tangent directions, right? So it's easy, okay? So once you have this matrix, the correspondences, we can define the energy, right? Because we have a locally explicit generative model, mesh, deforming mesh. And we can also have another loss, right, benefited from having having correspondences is to have the cycle consistency constraints among 3 adjacent synthetic shapes. So this adds some gradient regularizations, right, to the generative model, right, which has been used in active contours. Okay, some visual result. Okay, result regularization, right. If we have post derivations, the baseline doesn't work, right? It's a smooth interpolation, but it does not preserve deformation structure. With regularization, it does improve. Okay, so I want to skip how we got to the motivations of doing so to solve the correspondence problem, but I just want to show the pipeline. Okay, so the idea here is that we want to train a mesh generator. Okay, to feed the training data. Okay, then we find the nearest neighbor to find the intershape correspondences. Okay, so the way to do so is first we have the training shapes. We use the approach that I just introduced to interpolate those training shapes into a continuous shape space, right? But doing so using implicit representation, right? But once you have a complete continuous shape space, we can use this shape space to find a smooth interpolation between a template and any training shape, right? If you have a smooth interpolation, even the deformation between the training shape and the template is very big. But then you can use the smooth interpolation to guide the template, okay, to deform, right? Then we have a better, very good initial correspondences, right? Then we fine-tune, okay, the mesh generator to get correspondences, okay? So, without regularization to train the implicit generator, okay, this doesn't work at all, right? So it doesn't work. It's significantly worse to any baseline, okay, in terms of shape correspondences, okay? So the reason is that if the implicit shape generator is bad, then the template-based restoration will drift, okay? We have very bad initial correspondences, right? When doing the fine-tuning, you run into local minimum, right? If we have better initialization, we do fine-tuning, then it works, okay? So that is the idea, okay? I really like this paper, and the reason why this did not get an oral paper, actually, is because it's a very complicated pipeline, okay? Many viewers really like end-to-end, okay? They don't like this kind of three-stage. But I think this is a very complicated problem, right? I really do not know how to simplify, okay? If we really want to solve the correspondence problem, right? Right. So I want to spend 10 minutes on generative models, okay, for man-made shapes, okay? I think this is a very neat idea. Diffusion models, right, for visual generation has been trained, right? So it dominates like GAN and many early approaches, right? So very interesting is that when diffusion models came out, in the 3D community, people did not follow, okay? The reason was we actually did not know. Now we probably know, okay? We did not know how to define the so-called Gaussian distribution on the implicit representation, which has an infinite dimension, right? We need a finite dimension ambient space to define the Gaussian distribution. Now things change, okay? Okay, but 2 years ago, latent diffusion came out, right? So latent diffusion is very appealing because you can train an implicit decoder, right? You can train a point cloud decoder, volumetric decoder, okay? Any representation you want, right? So that is pre-trained. Then in the latent space, you do diffusion. You do not need you do need to worry about the representation issue in the latent space. Then in the 3D community people, wow, this is amazing, right? Right? Quite sad because we look at what image and video people do, right? Then we follow, right? I don't think this is a good thing, right? So 2 years I counted, even in this small area, right? Much smaller compared to image and video generation. 300 papers, okay, follow this, okay? 300 papers doing 3D generation under latent diffusion, okay? Right? So in the middle was a very strong baseline, right? Sigma paper last year. It's quite a strong baseline, right? If we run their code, still about 30% of the synthetic shapes have different issues, right? Like holes, disconnected shapes. So this is easy to understand, right? Because even you train a diffusion model in the latent space, you only use latent codes of 5,000 chairs, which are very, very sparse, right? But if you have a decoder, so this is a very important idea, okay? Very easy to understand. If you have a decoder, okay, for any latent code, you can get a 3D shape. If the 3D shape, for example, is disconnected, then you know that this particular latent code is very bad. When training the diffusion procedure, you should not sample the neighborhood of this latent code because it's bad, right? And we know this by checking the quality of the 3D shape. Of course, we can generalize this idea to quantify physical stability, geometric fidelity. Or you can model interactions between humans and 3D model, right? So for 3D shapes, we can define a quality checker, which is a continuous function in the latent space, right? Now, what we want to do is to train a better diffusion model by combining training instances and this quality check, which is continuous function, okay? Very simple idea, right? Now, if we're working in image generation, this is conceptually relevant, right? Many papers on this, okay? Classifier guidance or classifier field diffusion, which was introduced 3 years ago, not very long time ago, in image generation, right? And last year, 2 oral papers are the ICCV that human generation, right? Physical priors, right? Now, there are certain issues, right, to do this, right? First of all, in most cases, this is only applied in the sampling procedure, right? You train a diffusion model, then during sampling procedure, you use the classifier to guide the sampling procedure, right? If you do that, you're also exploring a trade-off between diversity and quality, right? We have this issue for GAN. Of course, this is much better than GAN, still there's certain issue, right? But we also need gradients of the classifier, right? You apply the gradient of classifier during the sampling procedure, right? So what we want to do here is to focus on training procedure. We want to train a better denoise network, right? And we do not want to use gradient, right? Because, for example, a shape is connected or not is a binary function. We do not have gradient, okay? Right? And for like other quantities, it's very complicated, right? Because we have to convert the gradient from the point cloud representation to the implicit representation. It's very complicated, okay? Right, so we want to do this without using the gradient, right? And train a better denoise network. So we use this pattern, right, EDM, which introduced at NERPS 2 years ago, right? A well-known paper. It has 3 contributions, right? First, it has a way to encode the denoise network. Secondly, it shows that setting the hyperparameters is very important, okay? The third contribution is what I just mentioned, right? You train a better denoise network, you get better images. You improve the sampling procedure, you also get better images. So we want to train better denoise network, right? By adding a loss. So the idea is very simple, right? In a batch, we have training instances. We also have some of the latent space that pass through the quality checker. Right? Of course, the question here is how to balance two sets of samples at different noise scales. Right? That is the biggest theoretical contribution. Right? I'm going to skip this. Okay, so we did some math. We have some rules. Okay, and if we do this, this accounts about 30% of improvement. Okay, still quite some improvement. Okay, but using the quality checker is very important. Okay, in terms of the quality checker, we did worst case structural analysis. Right, we optimize the worst case external force to quantify a shape is stable or not. So very interesting is that if you really want to figure out what is the weak vision of a shape, then you have to do this. But if you only care about the score, you only need eigenvalues of the stiffness matrix, right? For example, if the seventh eigenvalue is 0, then it's disconnected. If it's very small, it's not stable, right? But it doesn't tell you where the weak vision is, okay? So we did this, and we also trained a neural network to predict whether a shape has weird geometric structures, right? Because many physical stable shapes has those small holes, this thing can only be done by linear neural network, right? This is very different from GAN, right? Because in GAN, all the synthetic shapes are bad, right? Here we want to differentiate good synthetic shapes and bad synthetic shapes, okay? And very recently, we did this using foundation models, like vision models, right, without human labels, right? In this work, we actually ask humans to label, okay? Some result, right? We improved the FID and the KD scores by 20 to 30% for a very strong baseline, okay? And we do have some limitations, right? As mentioned, hyperparameter optimization accounts about 30% of improvement, and we cannot achieve perfect synthetic shapes, like all shapes are connected. The reason is that it's really bounded by the quality of the decoder, right? We are only improving the diffusion precision in the latent space. If the decoder is not very good, then we have to know very complicated latent diffusion, right? Which is still very difficult. Right now, we are working on improving the decoder, okay? So I want to skip this. I know I don't have time to go into this. Let me directly jump into conclusions, okay? So I think I showed you a few examples. I think 3D generative models are very different from image generative models, right? And because the application is very different. And I think this is a field where ML, the computer graphics, everything is synchronized, okay? We need push in both directions, right? Organizing workshops at both venues, very important. Many problems to work on, right? For how to enforce like this deformations in diffusion models, how to train a better decoder, right? That outputs physically stable shapes. Many open problems, okay? We are at a very early stage. So I really want to thank funding agencies and in particular one student who did some of those work I presented. Okay, thank you.
Thank you so much. Great talk. Now, questions?
Thank you, Professor, for your great talk. So in the last paper, so you've mentioned that you trained a quality checker.
Yeah.
So I was wondering that what's the difference between this quality checker to the GAN kind of a discriminator or yeah.
Because for the discriminator, is trained in an unsupervised manner, right? So it's essentially all the synthetic instances are negative, right, during training, and all the training instances are positive, right? So we have a series like model collapse issues, right? So here we have some, in particular in 3D generation, right? Why we want to use the discriminator because in the image space, we really do not know what is good, what is bad. We cannot ask humans to label. But in the 3D space, for certain quantities, we do, right? A shape is connected or not, right? And because of that, it's for synthetic shapes, we can differentiate good ones and bad ones. For discriminator, all the synthetic shapes are bad, right?
So
Right.
yeah, so then can we do just again? So all the synthetic 3D shapes are bad, and
But then you run into issues because in the very end, many synthetic images are already very good.
Okay.
But why you want to say they are bad in the next batch, right?
Yeah, that's
Right. So that is the issue, right? But for GAN, you cannot address that, right? Because you cannot label synthetic shapes, right? But for 3D generation, in particular in the latent distribution paradigm, we can actually label, right, bad synthetic shapes, good synthetic shapes, by running a quality checker. And we do have some result, in particular for GAN, right? Distribution alignment is not guaranteed, right? Only guaranteed in a very restricted space, right? For this, we really have some theoretical result, right? We have some under limited training data, right? We can reduce the variance. Right? I did not mention that, but it's kind of interesting.
Okay, thank you.
Right.
Thank you. Related. Can you actually still improve the quality checker using some active learning type of scenario?
Right. I think people also told me that this is relevant to reinforcement learning with human in the loop, right? Feedback. So what we did here is using a quality checker. Certainly, we only need samples. Okay, samples values. We did not use gradient. I believe the better strategy is to have some synergies between this and the people in the NLP community. Okay, many people do similar stuff, but do not talk to each other, right? So what we did here is very 3D specific, right? And we want to have something that human-free, right? Human labor-free, which if we want to include human feedback in the loop, then
Yeah, I guess my point maybe.
But I do want to mention is that it's relevant, okay? But on the other hand, this is quite intuitive, right? If you have a way to figure out whether something is good or not, right? Even under some limited cases. But really in the 3D space, in graphics, we have a lot of tools to quantify something, right? May not be differentiable, right? Differentiability is another issue, okay? It's a very complicated issue, right? But in terms of a score, that is pretty much very doable, right? So we do not do very complicated stuff because, for example, you can also model whether humans, right? Whether a shape can be interacted by a human, right? This can be also evaluated, right? We can do many things. Right.
We'll move the discussion offline, give opportunities to the other people. Do you have more questions from the audience?
Thanks. Yeah, I think the ARAP reg work went a little quick for me. I was just wondering if you could talk about again, like what representation are you applying it to?
Oh,
like,
mesh.
So there is a mesh representation.
Right, there's a mesh.
Because you were saying something about like a local implicit representation.
Oh, that
or like
is,
a local implicit correspondence
that
or
is,
something.
so
I
essentially,
think I'm
okay,
sorry,
okay.
I just missed the...
Yeah, I ran. So, this paper, the first paper, so this is a mesh, right? So this is a triangular mesh, right? So the output is a triangular mesh. Then we define the loss on this mesh representation. Then in the next paper, what we did is essentially we have an implicit representation, okay? We have implicit representation here. And when we developing the loss, we convert the implicit representation into a mesh locally, right? Because we have a mesh of this surface, we find the correspondences of the mesh vertices adjacent implicit surfaces, right? If we have that, locally we have a mesh parameterization, right? Then we can apply techniques in the first paper.
So the correspondence?
Right, correspondence.
Like nearest neighbor in a way?
Nearest is done by solving out. Right, so this is done by triangulating implicit surface, then we find the correspondences. Right, on adjacent implicit surfaces. So this is not easy, okay? Not easy, but this is doable. We take benefits from doing this locally, right? And because of that, we have a linear constraint, right? This is only well defined if the perturbation, the displacement is small, right? And deformation energy is only well defined if the magnitude in D is small, right? Otherwise, it's very difficult, okay?
So you have local correspondences?
Local correspondences.
For like nearby?
Right, nearby surfaces. Right.
And do you chain those together for like some sort of like correspondence between shapes that are...
Correspondences are defined by solving optimization problem. So essentially, this tau matrix is encoded by the network parameters of the implicit generative model, phi, right? So that depends on the implicit generator. Then we have V, we have the correspondences, then we have this deformation energy, right? So this deformation energy, phi is the parameters of the implicit generative model, right? And we do so by defining the correspondences and then plugging the deformation energy, right?
Thanks.
Right.
Let's wrap it up by one last question. If not, let me ask the last one. The regularization against fitting the data, that part is a little bit counterintuitive to machine learning people, because what's a regularization? The goal is to compete against fitting the data, right?
But for example, like, right, okay. Well, but certain regularizations, for example, like, maybe I should phrase in a slightly different way, right? Because there are better regularizations than regularizations. For example, the standard way is you add a smoothing regularization, right? And then if you increase the weight, if the weight is very big, then you drive the curve away from the data, right? If you actually know quite a lot about the data, you can have a better regularization, okay? But smoothing is still fine, right? It's not competing against fitting data. But the ARP regularization, you are minimizing the loss the deformation between any reconstruction and the template, that is against fitting the data. Okay? That is not smoothing at all, right? That is against. Smoothing is not against, but there are better smoothing techniques than weak ones, right?
That's great. Thank you so much. Let's maybe, yeah, thank the speaker again. Hello. Thank you.
Okay.